No, we will never leave Earth to reach the stars. It's August of 1492. Three small sailing ships set sail from the port of Palos de la Frontera, loaded with men, supplies, and hopes. The Santa María, the Pinta, and the Niña represent the entire universe of this expedition. Three fragile wooden shells disappearing into the vastness of the Atlantic, where no one knows what awaits them. These three ships carry just over 90 men, with provisions for a few months, rough navigation tools, and maps that are more legend than actual cartography. The distance Columbus is about to cover, several thousand nautical miles, is practically a breath compared to the distance that would separate humanity from the nearest star. Yet, this journey already seems on the edge of human endurance. Every meter of ocean is a gamble, and every day spent out of sight of land feels like an eternity of fear and waiting. Supplies are running low. Water becomes a nightmare. Men are falling ill, and the wood creaks under the pounding of the waves. Imagine a journey to Proxima Centauri, the closest star to our solar system. Means multiplying that challenge by millions. No longer just 90 men, but a whole world ship that would need to survive for generations. Not just a few months of sailing, but tens of thousands of years. Not just the risk of running out of supplies, but the necessity of rebuilding a complete ecosystem, of keeping an entire civilization alive in absolute emptiness. Columbus could see the horizon, feel the wind, and calculate the course. An interstellar journey, on the other hand, would mean surrendering to total darkness, to a distance so immense that even light would take years to cross it. And yet people, then as now, continue to dream the impossible. Let me make my position crystal clear. I'm deeply skeptical about the possibility of our species ever leaving the boundaries of the solar system to visit the stars. It's not exactly a popular stance, especially since, as a researcher dedicated to science communication, I often encounter people who are shocked or even offended by such a pessimistic and narrow-minded view of the future. These are the folks who accuse me of drawing hard, immovable lines around human progress. They never fail to remind me that the history of human innovation is packed with moments when the impossible became reality. They'll bring up Columbus, who set sail while being mocked by those laughing from the harbor docks, or the early 1900s, when so-called experts swore up and down that no machine heavier than air would ever take to the skies. And then, after a lengthy lecture, they'll usually conclude with something like this. See, both Columbus in 1492 and the Wright brothers in 1903 proved that those limits were nothing more than illusions created by human short-sightedness. All right, fair enough. Chapeau. But here is the crucial part they often overlook. Until about a century ago, the scientific method wasn't fully developed. Science back then was still a messy mix of intuition, popular beliefs, and rough trial and error. Just think about how, in the same era, many scientists still believed in the possibility of perpetual motion, chasing fantasies that would make even a middle schooler laugh today. Science isn't just a collection of innovations. It's a tool that has become sharper and more refined over time, helping us distinguish between what's truly possible and what belongs in the realm of the impossible. Today, with the vast body of physical knowledge we've accumulated, we can approach the idea of interstellar travel with a realism that isn't about pessimism, but about understanding the fundamental constraints of physics. The laws of physics aren't chains that bind us, they're maps that guide us. And those maps tell us that with current and foreseeable technologies, interstellar travel for humans is practically impossible. The distances are just too vast, the energy requirements are staggeringly high, and the risks to human life are overwhelming. Of course, this is just my opinion, and I wouldn't dare rule out the possibility of some future discovery, some technology so advanced it feels like magic, that could overturn everything we currently understand about the laws of physics. But here's the interesting part. Even if that were to happen, interstellar colonization wouldn't look anything like the historical models of colonization we're familiar with. We won't have ships packed with settlers, trade routes between distant stars, or mass migrations like we saw with the European colonization of the Americas or the westward expansion in the US. No, it would be something radically different. Maybe we'll send robotic probes or transmit genetic blueprints as data, or create artificial life forms capable of crossing space in ways we can't even begin to imagine today. The real frontier won't be physical. It'll be conceptual. We're talking about rethinking the very idea of travel, colonization, and existence itself. It's like going from the concept of a sailing ship to the idea of sending an instant message. A paradigm shift that goes far beyond mere technological innovation. Humanity will continue to push boundaries, that much is certain, but we'll do it in ways that are completely beyond our current understanding, just as medieval travelers could never have imagined airplanes or satellites. Our imagination is always one step behind the creativity of scientific evolution. In the end, perhaps the real conquest won't be reaching the stars, but continuing to look beyond the horizon with the same gaze that has always defined us. Part skepticism, part unshakable hope. But back on topic, we can reasonably say that humanity's expansion into interstellar space would be driven by three key goals: scientific exploration, the need for resources, the search for habitable planets in the case of catastrophic events that render Earth uninhabitable. The first point is one we can wholeheartedly support. Exploration, when understood as scientific research, must always be pursued, no matter what. And it's also the least complicated aspect of our activities in space. Increasingly intelligent robotic probes can do the job for us without requiring humans to land on planets as conquering demons or desperate colonists. But if we turn our attention to the second point, it's easy to see that there's no immediate need to leave our solar system. Not for now, at least, especially when you consider that between the Moon, asteroids, and Mars, we still have a wealth of resources to tap into right here where we are. As for the search for habitable planets, let's ask ourselves, what kind of catastrophe would be so dire that it pushes us to the stars? Overpopulation? During the 1960s and 1970s, at the height of the space age, the idea of humans and industries migrating to other celestial bodies seemed like a plausible solution to overpopulation and environmental degradation. Why worry about too many people on Earth, the thinking went, when we have the entire universe to expand into? After all, didn't Europe solve its demographic problems by sending its excess population to the New World discovered by Columbus? So why couldn't we just continue that process? Many scientists and advocates of space migration, Stephen Hawking, Robert Zubrin, Elon Musk, to name a few, have argued that becoming an interplanetary species is the only long-term defense against extinction. Whether the cause is man-made, climate change, nuclear war, etc., or cosmic, an asteroid impact, a gamma-ray burst, or some other cosmic phenomena, being tied to a single planet makes human civilization vulnerable. Okay, having a planet B to escape a cosmic threat sounds like a good idea. But let's be clear, not all of Earth's inhabitants would be able to relocate to some hypothetical new planet. At best, this would be a way to save, say, a few thousand humans, giving our species a chance to avoid extinction. But it certainly wouldn't mean salvation for everyone. Similarly, we also have to give up on the idea that overpopulation on Earth could be solved with a massive migration effort. To put this into perspective, consider this. The Earth's population currently grows by about 80 million people every year. If we wanted to maintain the current population size, we'd need to transport 80 million people to Mars or the Moon annually. An absolutely impossible feat, even with technology far more advanced than what we have today. In short, there's no escaping it. The solution to the enormous and often underestimated problem of overpopulation will have to come from within us, from our willingness to change. Let's say, for the sake of argument, that humanity decides to leave the solar system, whether for one of these reasons or all three combined, and sets its sight on one of the nearest stars. How would we do it? Hey guys, just a moment before we continue. Be sure to join the Insane Curiosity channel. Click on the bell, you'll help us to make products of even higher quality. If we're talking about a mission involving a human crew rather than sending small mechanical probes, we would obviously need to build spaceships capable of hosting dozens, if not hundreds of people. And even that won't be an easy feat. Also, what kind of propulsion system would these ships use? As we know, the main challenge in space exploration lies in the enormous distances between stars and the insurmountable limit imposed by the speed of light. Since we cannot exceed this speed, travel times with traditional propulsion systems, whether chemical or nuclear, could stretch to thousands of years, or for intergalactic journeys, even millions. On top of that, not only is it impossible to surpass the speed of light, but even achieving a significant fraction of that speed is a technological and scientific challenge of epic proportions. With today's technology, it would take thousands of years just to reach Proxima Centauri, which, let's remember, is the closest star. The others are vastly farther away. And still, even if you could, by some magical device, instantly reach the speed of light, it would still take 4.3 years to get there. This means that even traveling at the maximum speed possible in the universe, our species would be limited to exploratory trips in the immediate vicinity of the Sun, and would certainly not be able to establish a network of trade routes spanning the entire galaxy. But let's hypothesize that we want to colonize a suitable planet located 50 light-years away, ignoring all the objections raised so far about the feasibility of such an operation. How would we proceed? Given the travel times, the only feasible solution would be generation ships, a hypothetical type of large spacecraft capable of hosting, in a self-sufficient environment, hundreds or thousands of people, along with the animals necessary for food and for introducing an ecosystem to the planet we aim to colonize. Over the course of the journey, one generation would replace the previous one until the destination is reached. The challenges, of course, are plentiful. There are the technological issues of how to build a spacecraft capable of traveling for centuries through space without external assistance or replacement parts beyond what's already on board. Not to mention the energy source or propulsion system needed to move a ship of such size. Chemical rockets are out of the question. Nuclear energy is also impractical, and the laughable idea of solar sails could only work for microprobes. In short, we don't currently have any cards to play. Then there are the risks of the journey, such as micrometeoroids or radiation exposure. And finally, there's the human factor. The first generation would consist of volunteers, but subsequent generations would essentially be forced to continue the journey. Faced with these rather disheartening facts, some might point out that the travel times mentioned refer to those perceived by observers on Earth. The passengers aboard the spacecraft would measure a slightly shorter interval due to the time dilation predicted by special relativity. While it's reasonable to ignore the effects of time dilation for spacefarers traveling at 0.1 c, as the effect only accounts for 0.5%, it's true that the closer the speed gets to c, the more significant the effect becomes. For Earth-based observers, a spacecraft traveling to Epsilon Eridani at 0.99 c would reach its destination in 105 years. But for the passengers, the journey would take only 171 days. If it were possible to achieve speeds just shy of the speed of light, the traveler's journey would last only a fraction of a second, and visiting the farthest galaxies could be achieved within a human lifetime, though this would mean losing any temporal reference to their home planet. But as we've already stated, a massive generation ship could never travel at speeds exceeding 0.1 c, so there's no point in discussing it further. An alternative method might involve hibernating the crew, assuming that's even possible, or sending embryos that would later be raised by AI educational programs once the destination is reached. But you can't imagine the ethical debates surrounding such an operation, given the risks and the utter impracticality of having 1,000 children completely isolated on a planet 50 light-years away. And those wouldn't even be the only ethical concerns. A planet suitable for colonization would be one teeming with life, plants, animals, and ecosystems. Even setting aside planets inhabited by sentient species, those without civilizations might still be incompatible with our own ecosystem, resulting in the inevitable extinction of native life forms. There's also another issue. From here on Earth, it would be difficult for us to determine in advance which planets observed by telescopes are truly suitable for colonization. So what would we do? Would we have to set off blindly? Would we head towards a star, hoping that the faint signs of habitability detected by space telescopes turn out to be accurate? Certainly not. Given the costs and risks of interstellar travel, we couldn't just set off on an adventure. Both the journey and the destination would need to be meticulously planned. Any colonization mission would need to be preceded by one or more probes capable of pinpointing a suitable planet. So if we assume a suitable planet is 50 light-years away and launch a probe in the year 2100, the planet wouldn't be identified until after 2600. Any potential colonization mission would then arrive only after the year 3100. This makes it clear that solving Earth's destruction through the colonization of another planet is not a viable scenario. It would be far better to invest in technologies that can repair environmental damage or shift to a new economic development paradigm. But let's not give up so quickly. Maybe we're overlooking something. Yes, because mass isn't the only variable affected by speed in space travel. Another critical factor in relativistic journeys is time dilation. Unlike what classical physics assumes, time doesn't flow uniformly for all observers. It slows down the closer an observer moves to the speed of light. Skipping over the detailed physical and mathematical explanations, we have to trust the verified fact that on a spaceship leaving Earth and accelerating to relativistic speeds, time passes increasingly slower compared to the planet just left behind. Imagine a spacecraft traveling at 95% of the speed of light towards a planet 9.5 light-years away. An observer on Earth would measure the travel time as 10 years. For the crew members aboard the spacecraft, however, the journey would last only 3.12 years. In other words, between departure and arrival, the crew members would age just over 3 years, while 10 years would pass on Earth. If the speed reached 99% of the speed of light, time on board would pass 7 times more slowly. At 99.99% of the speed of light, time would pass 70 times more slowly. At 99.9999999% of the speed of light, time on board the spacecraft would pass 22,300 times more slowly than on Earth. And at 100% of the speed of light, time would appear to stop completely. These numbers, which might seem somewhat optimistic about the possibility of moving freely within the galaxy, reveal something surprising. They essentially tell us that for an observer traveling in a spacecraft at nearly 100% of the speed of light, their journey to any destination, whether 100 or 100,000 light-years away, would feel practically instantaneous. Incredible, right? If this were truly possible, we could realize the much-desired Star Trek scenario, where starships effortlessly travel from one point in the galaxy to another. So does time dilation solve the problem? Unfortunately, no. As we've seen earlier, accelerating a mass closer and closer to the speed of light would ultimately require an almost infinite amount of energy. No propulsion system currently known to us could grant us this gift. And even if the energy problem were somehow solved through methods we can't even begin to predict, a spacecraft traveling at the speed very close to the speed of light would face another significant danger. Space, as it turns out, isn't empty. It's filled with wandering atoms that sometimes gather into more complex forms like gas and dust from interstellar clouds, galaxies, stars, and planets. Other times, however, they remain as solitary atoms drifting aimlessly, likely not colliding with another atom for thousands of years. But there's a big difference between the probability of 2 hydrogen atoms colliding in a cubic centimeter of space and the certainty of the massive flow of particles that would collide with the spacecraft during its journey. These particles, mostly harmless at low speeds, transform into a deadly shower of projectiles and highly penetrating ionized radiation as velocity increases, capable of severely damaging the hull and making it dangerously radioactive for the crew. At speeds near the speed of light, these particles would gain such immense energy that they'd become lethal to any form of life on board. And that's not even considering the risk of passing through a thin veil of interstellar gas or dust, which could be enough to completely destroy the spacecraft. Some scientists believe that the mere presence of interstellar matter is sufficient to prevent a spacecraft from reaching speeds greater than 1/10 the speed of light. And as we've seen, such speeds are far from adequate to sustain a network of trade routes or large-scale exploration. Moreover, even if all these challenges were overcome, one insurmountable problem would remain. Time dilation would sever all ties between the traveling spacecraft and its home planet. Astronauts would depart knowing they'd never see their families, relatives, or friends again, unless they brought them along or didn't have any to begin with. Upon their return, they would find a society radically different from the one they had left behind. Not only that, a journey of this kind would not allow for the formation and existence of interstellar institutions, which rely on commercial and cultural exchanges between different races, assuming a homogeneous level of technological and social progress. Such homogeneity is incompatible with the timescales required for interstellar travel as currently conceived. What could possibly motivate a commercial enterprise to send its goods to the other end of the galaxy, knowing it would never again see or communicate with the spacecraft entrusted with its cargo? And what could drive the government of a planet to fund an interstellar mission from which it would never hear back, or one that would return to Earth long after the financiers themselves have been gone for millennia? Every spacecraft venturing into the realm of Einsteinian relativity would essentially become a world unto itself, without a homeland and without a past. Such an undertaking would raise profound questions about its validity and usefulness. What I'm trying to say is that in the absence of a technology indistinguishable from magic, a magical technology that furthermore seems to play fast and loose with the laws of physics as we understand them today, interstellar travel for humans is almost entirely impossible. And while I don't rule out the possibility that such a seemingly magical technology might emerge at some point in the future, the conclusion I draw is that if interstellar colonization were ever to happen, it wouldn't follow the historical pattern of colonization driven by mass migration and trade between colonies and the motherland. In short, it's pointless to dwell on it. Neither in the present nor in the foreseeable future is there any technology or cosmological shortcut capable of enabling us to make the great leap to the stars. Warp drives, Alcubierre propulsion, wormholes. Believe me, these are all baseless fantasies with no real foundation. And if anything of us ever reaches the stars, it won't be a representative of our species, but rather a robot or at most a transhuman. The only heirs of ours capable of traveling for millennia from one star to another in the galaxy. For what purpose, we can't even begin to imagine. We'll remain here, on this planet, forever, just as, quite likely, all other intelligent beings in the galaxy have resigned themselves to doing. Which might finally give us an answer to Enrico Fermi's great question: where is everybody? Those who take a conceptually optimistic view of the existence of intelligent life in space argue that the fact aliens aren't here isn't proof of their absence, but rather evidence that interstellar travel presents objectively insurmountable challenges for any level of technology. Physics offers no convenient shortcuts, such as the hypothetical wormholes that could directly connect vastly distant regions of the cosmos. In other words, even the most technologically advanced civilizations must resign themselves to colonizing only their own backyard. And while this might explain why they haven't visited us, it doesn't necessarily explain why we haven't detected any signs of their presence. Finally, there's one last consideration to add. The logic of colonization assumes a technological civilization driven by a plan of action projected millions of years into the future. Can you even imagine a political system drafting not a 5-year plan, not even a 10-year one, but one spanning millions of years to plan the colonization of the galaxy? And assuming that the supposed colonizers would go on to establish civilizations that would lose all contact with the mother civilization, and that this disconnection would repeat itself with every new planet colonized, how could the idea of a shared unified conquest be maintained across time and space? Far more likely, with each leap and each generation, the wave would splinter into even smaller streams, eventually fading out altogether. No, it's abundantly clear. If they aren't here physically, it's because the distances involved are simply too daunting, no matter the technological level of a civilization.